Hello. Uh, yeah. So good morning to all of you. Okay, so this is Prasad. Yeah. So some general rules for this session. So it's a request to everyone. Don't ask some general doubt and any particular questions from activity, practice, or graded. Those kind of doubts we can discuss in our sessions. Okay. So main thing is, ma'am will revise the concepts of concepts which are related to quiz 2, like counting principle, probability, and all. So you can ask doubt if you doubt in particular that concept and all. So don't ask any questions from activity graded and all. We can discuss those doubt in our session. Hope this point is clear to everyone. Yeah, ma'am. I think we can start. Yeah.
Good morning, Prashant. Good morning, everyone. Prashant, can we start?
Good morning, ma'am.
Good morning.
Yes, ma'am. Yes, ma'am. We can start. Am I audible? I think.
Yes,
Yes,
you're
ma'am.
audible. And have you given the instructions? You said you'll give some instructions.
Think I gave, right. I was audible or not? I'm not sure.
I couldn't hear that, but anyway, now I'm able to hear you. Okay, right.
Uh, okay, so let me repeat the ma'am, right? I think might be okay. So it's hello. Now I'm audible, right? Yeah. Okay.
Yeah.
Okay. Yeah.
Sir, you were
Okay.
audible in the
So
first time, right?
main rules are don't ask questions. Particular questions from activity, graded, practice, and all. We can discuss those kind of doubts in our session and TA session. Okay, so ma'am will revise the concepts related to quiz 2 and all. Okay, so you can ask doubt in particular concept, but don't ask any questions related from activity or any general doubts and all. Okay, those query
Okay.
we can handle in our session.
Okay. Thank you. Thank you, Prashant. And good morning, everyone. Am I audible? Is it clear?
Yes, ma'am. Yes, ma'am. Good morning, ma'am.
Thank you. Good morning. Good morning, everyone. Yeah. So this revision session is on the content of permutations, combinations, and probability. So what we are planning is it's just going to be again at a conceptual level, and I'm not going to look at particular examples, though I might use a couple of examples to just drive in the concepts, but predominantly it is going to be focused at a conceptual level of understanding these concepts. Now, you can use the chat box to ask your questions, and if there are anything I have missed, I think Prashant, you can just help me address if I have missed anything. Okay, I'll be following the chat box, but in even otherwise, if you think that I have missed out on something, please let me know. So the agenda or the plan for today is the following. I'm planning to start with the basic rules of counting, and then we'll introduce the concepts behind permutation, combination, and we look at a simple example of permutation and combination. Predominantly, I think many of the learners are finding challenge in understanding where to use a permutation and where to use a combination. So we'll try and address that aspect a bit. Then we move on to the concept of probability. We introduce the building blocks there, which are random experiment, sample space, events, the properties of probability. Then afterwards, we have the additional rule, and conditional probability leads to what we call the multiplication rule. And finally, we stop with Bayes theorem. Now, something that was not introduced in the notes is the notion of probability trees, which is a very simple tool to try and understand how to assign probabilities, and we are going to just touch upon that tool also. So all of you are ready to go? We'll start?
Yes, ma'am.
Okay, good.
Yes, ma'am.
So we started our discussion on permutations and combinations with what we refer to as the addition rule of counting and the multiplication rule of counting. Now, to illustrate it, suppose you can see that I am asking you, I have two options. One is I have a yellow shirt, an orange shirt, and a green shirt. And in another bucket, I have a black pant and a blue pant. If I'm asking you to choose a shirt or a pant, how many ways can you do it? I can either choose a yellow shirt, an orange shirt, or a green shirt, and there are 3 ways of choosing it. Or I can choose a black pant or a blue pant. There are 2 ways of choosing a pant, and the way I can choose a shirt, one shirt or a pant is 3 plus 2, which is 5 ways. On the other hand, if I want you to choose from this bucket a shirt and from this bucket a pant, I can choose a shirt in 3 ways. I can choose a pant in 2 ways. And I can choose a combination of a shirt and pant, which could be yellow and black or yellow and blue, red and black or red and blue, green and black or green and blue. So the total number of ways I can do it is 3 into 2, which is 6 ways. So the first thing is what we refer to as the addition rule in counting. That is, if an action A can happen in n1 different ways. Here that action A was choosing a shirt, and that could have happened in 3 ways. The action B was choosing a pant, and that action could happen in 2 ways. The total number of ways and I can choose a shirt or a pant was 3 plus 2, which was 5 ways. Similarly, when I refer to the second point, where I could have again choosing a shirt, which was in 3 ways, choosing a pant in 2 ways, the number of ways I can choose a shirt and a pant is nothing but 3 into 2, which was 6 ways, and that was what we refer to as the multiplication rule. Now this I can extend it to n1 plus n2. If I have multiple actions, say k action, the addition rule can be extended to k actions. Similarly, the multiplication rule also can be extended to k actions. So this is the basic rule of counting. And B, whenever your question is A or B, then you apply addition rule. Whenever it is A and B, you'll apply multiplication rule. This is conceptually clear. Yeah?
Yes, ma'am.
Yes, ma'am.
Okay, ma'am. Yes, ma'am.
So you can use the chat box also if there is any doubt. I am following the chat box. Right? So whenever you are encountering questions like, okay, you find out how many words can be formed, then after you know that, you use either the multiplication rule. In all the problems that you can see on the screen, for example, in the first one, if repetition is not allowed, how many words can be formed? Repetition is not allowed. How many ways can I choose the first one? First alphabet. So I have 4 places. The first one can be chosen in 4 ways. The second one, blank, can be filled in 3 ways. The third, so it would be 4 into 3 into 2 into 1. Okay. And then afterwards, you can see that how many 2-digit even numbers can be formed. So to form 2-digit even numbers, I can either have a 2 here. If I have a 2 here and I allow digits to be repeated, I have 5 ways of filling this up. If I have 4 here, I again have 5 ways of filling it up. So I have a 5 plus 2 in plus 5 plus 4. That is the total number of ways of forming 2-digit even numbers. Okay. So you can see that these are simple application of my addition rule. Now from this addition rule, we go and we apply this basic rule of counting, this addition and multiplication. In particular, we are going to be focused only on the multiplication rule to come up with a notion of what we refer to as a factorial. Okay. So when you look at the factorial, I am looking at nothing but I have n blocks. This first one can be filled in n ways. The second can be filled in n minus 1 ways. This can be filled in n minus 2. This is n minus 3. So forth 1. The total number of ways I can fill all of this is applying multiplication rule. So I get a n into n minus 1, and this is referred to as a n factorial. So this n factorial notation is coming to us to help us. We introduce the notation of a factorial, and then we introduce what is a permutation. Now, when we talk about a permutation, permutation is nothing but an ordered arrangement. What do we mean by an ordered arrangement? So suppose I have R objects, Okay. And I have to look at arranging these R objects from N objects. So I have 1, 2, 3 up to R. How many ways can I fill up this? And they are N distinct objects. How many ways can I fill up the first block? I have N distinct objects. I can fill this in N way. This can be in N minus 1. This will be N minus 2. So this will be N minus of R minus 1. Is that right? Which
Yes,
is nothing but N minus R plus 1. So this is nothing but N minus of R minus 1 is nothing but N minus R plus 1. I apply the multiplication rule. It's N into N minus 1 into N minus R plus 1. Now I can multiply this numerator with N minus R into N minus R minus 1 up to 1. So this portion is nothing but N minus R factorial. Would you agree? N minus R into N minus R minus 1 up to 1 is N minus R factorial. So yes, if I'm going to multiply and divide with the same number, so I have in my denominator N minus R factorial, this portion which I originally had is what we refer to as the permutation of R objects from a collection of N objects that is given by N factorial into N minus R factorial. And this is how we derive the same. Okay. So this at a conceptual level, this is how I have N distinct objects. Now this distinction is very, very important. I'm having N distinct objects and I'm looking at the number of possible permutations of N distinct objects from this collection of N objects. Now, if R is 0, this N minus 0 is what I have. So, N factorial divided by N factorial would be 1. So, I have only one ordered arrangement. That is, how many ways can I choose one object from N objects? How many ways can I choose one object given a choice of N objects? I can do it in one object. No objects. If I cannot choose this one, there's only one ordered arrangement of 0. There are N ways of choosing N objects and NP of one object or from N objects and N distinct objects. This is NPN, which is N factorial into N factorial. We know that given 3 objects, okay, if N equal to 3, let it be ABC, I can write it as ABC. I can write it as ACB. I can write it as BAC. Okay. I can write it as BCA. I can write it as CAB. And I can write it as CBA. So I have 1, 2, 3, 4, 5, 6, which is nothing but 3 factorial, which is 3 into 2. So I have so many distinct ways of. So the first formula when we have and we understand permutation is this formula where I have N distinct objects, okay, that is A, B, C are distinct, and I'm looking at the possible permutations of our objects. Suppose I take 2 objects, I know it is just A, B, B, A, A, C, okay, C, A, B, C, and C, B. So they are distinct. AB is distinct from BA, AC is distinct from CA, and BC is distinct from CB. So this is distinct objects is very important for me to understand. Now, moving forward, if I'm not interested in distinct objects, is my screen visible? I think it had gone over. Is the screen visible?
Yes, ma'am. Screen is visible.
Yes, ma'am.
So now suppose in the earlier case, I did not allow repetition. So because I did not allow repetition, if I have say 3 blanks, if I could fill this with N, I could fill this up with N minus 1 because I lost that 1 which had already gone here. But now suppose I'm allowing repetition, the first blank can be filled in N possible ways. The second can also be filled in N possible ways. The third can also be filled in N possible ways. So if I have R blanks, each one of this can be filled in N ways. So the total number of ways it can be filled is N to the power of R. This is when repetition not allowed. This is when repetition is allowed. This would be n minus 2. And this is n minus r minus 1. This is what I said was npr. This is n to the power r. So when I have distinct objects, I can either allow repetitions or I cannot allow repetitions. When I do not allow repetition, I use the NPR formula. When I allow repetition, I use n to the power of r formula. Till here, is it clear? Now, the next thing is what
Yes,
would
ma'am.
happen
Yes, ma'am.
if the objects are not distinct. So you will always have problems where I'll ask you how many words can I, how many ways can I arrange words of, say, statistics. Here I do not have distinct. Whereas if I look at a word called able, they are all distinct. Okay. Whereas when I have statistics, I have 3 T's, S's, 2 T's, I have 3 T's, I have 2 I's, 1 C, and 1 A. So they are not distinct. So when I need to now understand how to do this when the objects are not distinct. So the idea behind this is, suppose I have again n objects. So let's look at statistics. 1, 2, 3, 4, 5, 6. Or let me look at data. Okay. Here I have, when I look at data, again I have 4 objects, but only I have 3 distinct objects. And what are the 3 distinct ones? It is D, T, and A. Is this clear? Because A is repeating.
Yes, ma'am.
Yes, ma'am.
So I have 4 objects, of which 2 of them are of one kind and the others are the same. So the question is, how many ways can I do this permutation? The idea here is, now when I have all of them distinct, suppose I had a DA, TA, A1 and A2, then this D, A2, T, A1 and these two are the same. Would you all agree?
Yeah, ma'am.
Yes, ma'am.
Yes,
These
ma'am.
two are the same. So
No,
what happens is, because these two are the same, I need to consider them as one. I need to divide. That's why I am dividing that with P fact. P of them is of one kind. So 2 of them are of one kind, because A1 and A2 between themselves can be, and A2, A1, they are the same. Even though I'm writing it as A1, A2 are basically the same element. So I need to divide it. So when I have P of them, I have 2 of them of one kind. This becomes 4 factorial by 2 factorial. Now suppose I can extend the same idea to look at permutations of n objects where P1 is of one kind, P2 is of second kind, and Pk is of the third kind. That would just give me n factorial by P1 factorial, P2 factorial, Pk factorial. So whenever you have questions where you have, again it is permutation of distinct objects, but here I have a subset of objects of the same kind, you will use the formula. Suppose I have now, this is the general formula. Now, if I have only a one kind, it will reduce to n factorial by P1 factorial, which is the same as what we gave earlier. If I have 2 kinds, it will be n factorial by P1 factorial, P2 factorial. So when I look at statistics, my n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my n is 10. I have P1, which is the number of S's, is of 3. P2, T is 3. P3, I is 2. P4, whether I'm having P3 is 1 or P4, the order doesn't matter to me here. P4, so this is S, this is T, this is I, this is C, which is just 1. Okay, and I have statistics. So A is also only 1. Okay, so I have the number of ways I can apply, or I can arrange this as 10 factorial by 3 factorial, 3 factorial, 1 factorial, 2 factorial, and 1 factorial. So this is the number of ways a permutation can be done when my objects are distinct. I allow repetitions, I do not allow repetitions, and when a subset of objects are of the same kind. Any questions till here?
No, ma'am.
No, ma'am.
So the next important concept is that of circular permutation. So we saw that typically I have n objects. If I am looking at arranging r objects, okay, this is NPR, okay, where I am not allowing repetitions. N to the R, allowing repetition. In this, n with distinct, n factorial by p1 factorial, p2 factorial, pk factorial, when not all of them are distinct. These are the three important formula. Now, how do I look at it when I move from a linear? So what we looked here was arrangement in a line. So they are also referred to as linear permutations. Now, what would happen when I move from a linear to a circular permutation? So in this, we always encounter problem that people are sitting in a round table. Now, what happens in a circular permutation is, see, for example, if I am fixing this person in a table and I am arranging these people A, B, C, D. Okay, this is one way of arrangement. Now, this arrangement is same as the arrangement B, C, D, A. Would you all agree or is it different?
Agree, ma'am.
Same, ma'am.
It's the same.
It's same.
So when I am looking, but in a linear fashion, this ABCD is not the same as BCDA. Agreed? In the linear permutation, they are different.
Yes,
Yes.
ma'am.
Sitting
Yes,
in a,
ma'am.
so I cannot apply the linear permutation formula to circular permutation. So what I need to do is, the way I look at it is, again, I have n distinct objects. Now, when I come to circular permutation, the distinction I make is whether the clockwise and anti-clockwise are different. Okay, so if this is the case where clockwise and anti-clockwise are different, you can see that the number of ways, here I have 4 people. So the idea is you fix one of them. If I fix one of them, okay, now the other 3 between them, how many ways can I arrange? If I fix one of them, the other 3 I can
3
arrange.
factorial.
3 factorial. In general, if I have n objects and I fix one of them, fix the position of one of them, in how many
n
other?
minus 1 factorial.
N minus 1
N
factorial.
minus 1
So
factorial.
that is what I have here. That is the number of distinct objects that can be arranged in a circle where the clockwise and anti-clockwise are different is n minus 1 factorial. Okay. Now, if the clockwise and anti-clockwise are the same, okay, so this is the clockwise A, B, C, D, A to B, B to C, C to D, and D to A. Now, anti-clockwise is A to B, B to D, D to C. So, A, B, C, D, these two are the same. If anti-clockwise and clockwise are the same,
Yes, yes, ma'am.
right? So, if I go back here, A to B, B to C, C to D, and this A to B, these two are the same. Similarly, these two are the same. These two are the same. So when the clockwise and anti-clockwise are the same, okay, and this is when you can have the number of permutation is just n minus 1 factorial by 2. Now, where do you apply this? This is applied in problems where you are asked to find out how many ways I can. If you fix 2 people, yes. If I fix 2 people, so now the idea is, okay, let me look at this. A, B, C, D. I am fixing B and C together, right? So if I fix A, how many ways can, and B and C are always together. How many ways can I can have B and C are as the same unit, right?
2 ways, ma'am.
2 factorial.
2 ways.
And either B, C. Within B and C, how many ways can I do that?
2 again.
2 ways. Is that clear? right?
Yes,
So that
ma'am.
it's the same as linear. The only conceptual understanding you need to do is I fix one of them. I cannot fix B and C then. Even if I fix B and C together, okay, it can be A here or B here if clockwise is different, or sorry, D here. I'm fixing BC here, or it is A and D here, and between B and C, I can have a CB also. Is that right?
Yes, ma'am.
Yes, ma'am.
Listen. So that is the understanding is what is it I'm looking at? Always try and see whether I can convert it. Say, and what do I know? I know linear permutations. I know how to do the linear permutation when I'm forcing two of them are together always. Right? Now that would be a single unit which I'm going to fix, and based on that, I'm going to take decisions. Does that make sense?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Right?
Yes, ma'am.
Yes,
So now, where are the applications of this? You can see that making a garland of beads, different colors of beads. I want beads of the same color to be together. I want men and women are seated on a round table. Men are together or men are not together. All these things you should apply the formula. For example, even in linear thing, they'll say that no two people have to stay together. How will you apply this permutation to look at this counting? No
Total
two.
minus 2 people sit together.
So there are multiple ways to do it. You'll find out the total number of ways. You'll find out first you'll find out the total number of ways I can have these. Okay. Then I'll say that, okay, these two people are always together, and I can subtract the first minus the second. That would give me the number of ways where these two people are never together. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
yes, ma'am.
Yeah. So that's what I'm saying, next to each other. So when I suppose, see, let's look at a circular, let me look at this case. Once again, let me, suppose I have A, B, C, D. Okay, let's look at the linear permutation. How many ways can I arrange these four people?
4 factorial. 4
Four
factorial.
factorial. Agreed. In how many ways
Yes, ma'am.
will B and C always sit together? How do you address these problems?
Subtract the ways where the both cannot
Just
sit
3
together.
factorial. B and C are always together, so I'll consider B and C as one unit. So it will be A, B, C, D. Okay, so I have 3 units, right? It would be 3 factorial. But between B and C,
2. 3
Wait,
factorial into 2.
into 2 factorial, right? Would you all agree? Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Consider B and C as in sitting as a unit, then A, B, C, D. Okay, D, B, C, A, B, C, A, D, B, C, D, A. Okay, A, D, B, C, D, A, B, C. These are the ways. Is that right?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Now, each one of them I can do a C, B, D, B, C, B, D, right? So, for each one of them, I have a CB also. Would you all agree?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
The total number of ways will be 3 factorial into 2 factorial.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So, if I have n objects where R of them are always together, then what is the total number of ways I can arrange them?
N factorial into R factorial.
The 10 factorial?
N
Will it be
minus R factorial
N
into R
minus R.
factorial.
Yes,
it's not
ma'am.
n factorial, right? This
N
R of
minus
them
1.
are always together. So how did you get this 3 factorial? N is 4, right? You did
Yes,
not
ma'am.
4 factorial. Is that clear?
Yes, ma'am.
Yes, ma'am.
It's not n factorial, right? If I have n objects in which I'm insisting that R of them should always to be together, okay? So I'll have n minus R is what? See, here n was 4. I insisted that these two should be together, right?
Yes, ma'am.
Yes,
So
ma'am.
I had
Yes,
so I'm having this R is 2 here. So n minus r plus 1 factorial into r factorial. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Ma'am.
Right? Because this one I should see n minus r is the other one, and this plus 1, which is this block, r factorial
ma'am.
into r factorial. Is this clear? No. How to address this? But this was a linear permutation. Now I'm going to ask the same thing when it is a circle. That is the question that you asked, right? Two people sit together and all of that.
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Now in a circle, what would be the thing? Same notation would be the same, right? The idea is the same. In a circle, what happened earlier? See, when I had 4 people, how many ways could I seat them in a circle?
3
3
factorial.
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 N minus 1 factorial, right? In a line,
Yes,
it
ma'am.
was n factorial. Agreed?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now
Yes,
I'm
ma'am.
having B and C together. So this would be again n minus r plus 1 minus 1 factorial. Is that right?
Yes, ma'am.
Yes.
Yes, ma'am.
N minus r factorial. And between them, I can do it in another way. That would be, so n minus r
Factorial.
factorial into r factorial. Is it clear?
Yes, ma'am.
Yes, ma'am. Yes.
Now I can move forward, and this was the so this n minus r plus 1 factorial into r factorial is the number of ways these two people will always be together. But suppose I give you a situation where these people should never be together. What would be the total number of ways to do it?
Total minus when they are together.
Total minus they are together.
That's simple, right? I know, so I have n factorial is the total number of ways 4 people can be arranged. N minus r plus 1 factorial into r factorial is the number of ways this n people can be arranged. These r people are always together. So the difference would be the total number of ways these people are not together. Is that clear?
Yes,
Yes.
ma'am.
Yes, ma'am.
Yes, ma'am.
This one, suppose I have R1 of one kind and R2 of the other kind. And then I have n people. That is, I want B and C to be together and A and D also to be together. How many ways can I arrange?
2 ways.
2 ways? 2 ways?
And again 2.
Is it 2 ways? I can arrange BCAD or ADBC. That's it?
And CB.
Ma'am, 8. 8.
ADCB
Again, they
do DACB. Agreed?
Yes, ma'am.
So be 2 into 2, right?
Yes, ma'am.
TA. BCAD, BCDA. Okay.
Ma'am,
Similarly-
here BC and DA are fixed.
Yeah, B and C and A and D are always together. So how many ways can I arrange?
Okay.
B and C are always together. How many ways can I arrange them? So suppose I have I have girl 1, girl 2, boy 1, boy 2. I'm saying the girls and boys are always together. How many ways can I arrange them?
4 ways.
Only 4 ways? Think about it. How many ways?
Ma'am, 8. Ma'am, 2 is individually, then girls and boys
See, if I
could be
think
arranged
of
in 2 ways.
this is one, this is, how many ways can I arrange this blocks together? So either G1,
2
G2
ways.
for B1, B2 or B1, B2, G1, G2, right?
Ma'am, total 8
Yeah.
ways.
How?
8 ways.
And 4
We
factorial.
can
And we also
make
have to interchange within the
Yes,
like
so
Yeah,
this,
boxes as
this
well,
will
yeah.
give me, this will be G1, G2, B1, B2, G1, G2, B2, B1. If girls are first, right? And G2, G1, B1, B2, right? And G2, G1, B2, B1. Each one is going to give me 4 ways. So this will again give me 4 ways. So total 8 ways. Why is it 16 ways? What? Just enumerate it. See, G1, G2, B1, B2, right? G1, G2, B2, B1. G2, G1, B1, B2. From this, if girls are first and boys are second. So 8 ways, right? With boys first and girls second. Is that clear?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
So this, so now if it's starting with the same thing in a circular form, this one. So everything you fix the girls and boys within themselves, how they can be arranged. Okay. And this one circular would be circular. How many ways can I do that? So whenever in doubt, my suggestion is just take a small problem and work it out. Okay. So that you'll know at a conceptual level whether it is correct or wrong. You can enumerate it. And then now this I can include it. Suppose I have n items where R1 is of one kind, R2 is of the other kind, and they have to be together. How many ways will I be able to write it? Put them in. That's all it is, right? So this would be, how would I look at it? Initially, I said n items and R of one kind. You said n minus R plus 1 factorial into R factorial. Agreed? Now I'm saying R1 is of one kind and R2 of the other kind. You can extend this. That's what I'm trying to say. Is it clear?
Yes, ma'am.
Yes.
Yes, ma'am.
Yes, ma'am.
4 ways, I guess.
This is about permutation. Now, when the arrangement is not important. Okay, so for example, when I had A, B, C, B, A, C, B, C, A, all of them are this, or from A, B, C, I'm taking only two. I could do an A, B. I said I could do a B, A. I could do an A, C. I could do a C, A. I could do a B, C. I could do a C, B. Okay, when I'm choosing two. But A, B and B, A, when I'm choosing two and not arranging two, these are all the same, right? When I'm choosing two and not arranging two, I have two of them. Two of my permutation will just give me a combination. So what I will do is, and I have n p r is n factorial by n minus r factorial. Is that right?
Yes, ma'am.
Yes, ma'am.
Each of this NPR. So I have, these are the total number of permutations of R. This is the arrangement. I divide each one of them with R factorial because this is 2 factorial ways of doing it and 2 is going to contribute to 1. So if I had C, A, B, C, B, A, C, B, C, A and all of them, A, C, B, all of them are going to contribute to 1. So I divide it with the total number of this R factorial and I'll get that is NCR. So you can see that NCR is n factorial by n minus r factorial. Basically, it is NPR divided by r factorial, or NPR is r factorial into n choose r. So this n choose r is what we refer to as a binomial coefficient. And what is that? N choose r is nothing but n factorial by n minus r factorial to r factorial. This is the definition of n choose r. Now we have, I'm not going to go through these important results because this is n choose r is same as n choose n minus r. Okay. So there is something said in 100 student, I'm not able to understand what it is. Okay, anyway, if there's nothing with respect to my course, and n choose n is equal to 1, n choose 0 is equal to 1. And the most important one identity, which I have already proved, is n choose r is n minus 1 choose r minus 1 plus n minus 1 choose r. This has been already proved in the class. This is a very important binomial identity. What this says is, if I want to choose r objects from n objects, okay, the way I can write it is this n minus 1 choose r minus 1 plus n minus 1 choose r. This has already been explained in the thing. This is in my course. You can just go through it. It's an important binomial identity. N minus r plus 1. How are we adding 1 to it? If you're referring to 1, 2, 3, 4, 5, 6, 7, and I say I have n objects, let me look at 5 objects of which 2 of the same kind. Okay, 2 are always together. Okay, I have 1, 2, 3, 4, 5. Let me say A, B, C, D, E. B and C are always together. So if B and C are always together, how many ways, how many objects will I have? If I consider B and C as 1, how many do I have?
4.
4, right? So my N is equal to 5, my R is 2. It will always be 5 minus R, N minus R is going to be the number of objects without this, and this has to be considered. So it's an N minus R plus 1. Is that clear?
Yes.
Minus R is the number of objects which are distinct and not together. Not distinct, they are not together. And this together is considered as 1. So I have N minus R plus 1. Is that clear? That's how I got a N minus R plus 1.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yeah, right. So now the key idea and what you are tested on, be it the assignment or activity or an exam, is where to use permutation and where to use combination. This is one of the main challenges which many learners have, and I'll try and address that in the next few minutes. So let's look at the case where I want to create a password. Okay, and a password consists of 7 characters. Order matters. Whenever you have a password, definitely order matters, right? Is a password, for example, this password where I just have 2, 3, 4, 5 and 2, 4, 3, 5. Are they the same? If, when you are getting an OTP, 4-number OTP, or are they different?
Different.
No, ma'am.
And so
No, ma'am.
whenever you have passwords, okay, the order matters. So suppose you are a hacker and you want to hack a 4-digit OTP. How many times should you, how many possible combinations are there?
4 factorial.
4 factorial.
How many base? 4-digit factor, this one, lock. So that's what I'm trying to say. If I have a 4-digit lock, I don't know whether I have that here. Yeah, 4-digit lock. Okay, or ABCD. With ABCD, but I'm having a numerical. In the how many can come in my first way? I'm allowing 0 also. In the first thing, how many ways can I do it? I'm
10.
allowing repetitions
10.
also.
10 ways.
10. Second,
9 ways.
10.
I'm allowing repetition. If I don't allow repetition, I have
10.
9 ways.
10.
Yeah,
Okay,
about 10 ways.
This,
10.
10 ways.
this.
Again
10.
10. Also 10.
Total number of codes that can be generated would be
10 to the power 4. 10 to the 4.
right. It is 10 to the power of 4. Is that clear? Right?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Do not allow repetition.
Then 10
10
ways.
C4.
9 into 8 into 7.
7.
Right?
7.
Okay,
Yes,
so
ma'am.
you can see that these are the possible number of codes that can be generated. So whenever you're looking, now where do you apply this? You see that most of your thing, your phone or anything will get locked after 3 attempts. Is that right? Many
Yes,
times
ma'am.
you keep entering the wrong password. It's not that you keep entering a password and even if you have the time and energy to do this 10 to the power of 4 attempts and get the right one, the password will lock itself and they'll ask you to change the password, right? Is
Yes,
that right?
ma'am.
Yes, ma'am.
So you can see that that is where the security comes from. So you see that in 3 attempts and the chance of you, so we'll talk about this in probability. So that's why you need this counting. The chance of you hacking it in the first attempt will be very, very minimal. Agreed? Because only
Yes,
one out of 10 to the power of 4 is going to be right. And
Yes,
that's the chance of you getting it in the first attempt. So the probability of you hacking it in the first thing is very, very low. So when you are looking at a permutation or combination, typically when you are looking at problems which say that you need a password or a code, you will be using typically a permutation. Is that clear?
yes, ma'am.
Yes, ma'am.
Yes,
On the
ma'am.
other hand, suppose you have problems like, for example, you have now, I'm sure that all of you who have been using Swiggy and Zomato and everything, if you want to order a pizza or something, you have some options which are saying build your own choose your toppings. Have you seen this?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
You
Yes,
have
ma'am.
an option, choose your
Yes,
toppings.
ma'am.
Right? They give you a set of toppings. Or even if you're ordering from North Indian restaurants and everything, they say that, okay, choose your starters, choose your main course, whether you want roti, choose your rotis and all of that. So here, does the order make any sense? Will it make sense that I'm choosing capsicum before I'm choosing corn, before I'm choosing...
It will not
No,
make it.
no, ma'am.
The
No,
order
ma'am.
does not matter, right? So
Yes,
from
ma'am.
topics, if they're asking you to choose, the order does not matter unless you are going to specify that, okay, first capsicum, on top of it you put tomatoes, on top of it you put corn. I don't think any pizza company is going to listen to you if you ask them. They're
Yes, ma'am.
asking you for a choice, right? In this
Yes, ma'am.
case, when there are similarly, so the same idea, when you have a choice of 10 subjects and they're asking you to choose 5 electives, will it be a permutation or a combination?
Combination.
It will be a combination. So depending on the context of the problem, you need to understand whether you are going to apply a permutation or a combination. Wherever the order is important, you will go with a permutation. Wherever the order is not important, you will go with a combination. Okay. So this will, you need to practice a lot. I would only say that this is not a, don't feel bad if you don't get the concept at the first go. Permutation and combination have been not only in India, it universally troubles a lot of people. Okay. And the only way to overcome this fear for permutation and combination is through doing a lot of problems till you are able to identify it properly and you are able to crack it. Is that clear?
Yes, ma'am.
Yes, ma'am.
Don't get disheartened if you're not able to see it in the first go or something. This counting, permutations and combination, in my experience as a teacher, this has been a topic which many people are challenged the first time. But as you keep looking at problems and as you keep solving more of them, you start getting a comfort level. So understand it at a conceptual level. That is what I would recommend. Okay. So now the third thing is where you forming a code. I said again, it's a permutation. Now let's look at this. A bookshelf has 8 different books. If I'm interested in arranging 5 books on a shelf, okay, would I go with a permutation or combination?
Permutation.
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 I'm saying arranging. It makes a difference whether I'm arranging it. But if I'm asking you to choose 5 books from these 8 books, it would be
Combination.
it does not matter. Okay. And one of the most popular problems, and I'm sure you also would have seen a population problem here, is this forming or choosing teams. Okay. So if the team roles, members or positions are distinct, order of selection matters. So for example, look at the company. So if I'm asking, in how many ways can a committee of 4 members be selected from a group of 10 people? Is this a permutation or is it a combination? Is the position mentioned here? Is the role mentioned here?
No, ma'am. Here is a
Combination.
combination, ma'am.
Combination.
I tell you that a committee of 4 members be selected from a group of 10 people to hold specific positions.
Order matters.
Permutation.
Okay. Now let me ask you, how are sports, when I'm selecting sports teams, do I use permutation or do I use combination? I want to select a cricket team.
Combination.
Are you sure?
Ma'am, permutation.
When I select all 11 batsmen, will that be a good team?
No, ma'am.
No.
Huh?
But you didn't specify you have to take
I didn't specify, but I thought you all knew cricket more than I knew.
But if it's given total number of
Suppose
bowlers
I
and
have-
total batsmen.
Suppose I have a pool of 30 people and I want to make a team. Should I specify whether it's a permutation or combination? Or is it
would be
inherent
both.
that you would want the few batters, few this one? How would I do it?
Ma'am, you have to specify that there are a number of batsmen and number of bowlers, and then we can choose from them to make our team.
I should specify, right?
Yeah.
But there, then the roles are very specific, right? Yeah. Huh? I can't hear you. Okay, I think it was not addressed.
Yeah.
Yeah. Okay. Right. So this is what I would. So yeah. So I need to specify it. I agree completely if I say okay. Choose. Suppose I say choose players. 10 players from a pool of 50 players. That would be just 50. Choose 10. But if I
Yes,
want
ma'am.
to choose a team, I need to specify again what are the roles I'm looking at. Is that right?
Yes,
Yes,
ma'am.
ma'am.
Slightly more difficult because I need to specify out of the population pool how many are batsmen, how many are all-rounders, how many are bowlers. Within bowlers, I need to specify how many are spin, how many are pace. Okay, all of this would matter, right?
Right.
Yes,
ma'am.
Yes, ma'am.
Yes,
Then
ma'am.
you know how to form. So you can make a living if you crack this. If you have just seen the recently concluded World Cup, you see every celebrity coming up with their own teams, right? Every time people
Yes.
say, okay, this is my best 11, that is my best 11, and all of that. So how many ways can those best 11s be formed? And no two celebrities will agree on the same 11, right? Yeah?
Yes, ma'am.
Yes, ma'am.
Yeah.
Yes, ma'am.
Okay. So when you're looking at permutation and combination, first understand at a conceptual level what is a permutation, what is a combination, and then when the order matters or when the arrangement matters, you'll go in for a permutation. When it does not matter, you'll go in for a combination. Any questions with respect to this permutation and combination? Or
Yes, ma'am.
is it clear at a
Ma'am,
combination?
I have.
Yeah, please. Yeah.
Ma'am, in the first question,
Hmm.
ma'am, I didn't get the exact we had to use A to Z small letters, lowercase letters, and then
Yeah.
0 to 9, and we had to form a 7-character password.
Yes.
So then why did we choose four we treat it as 4 spaces to be filled out of 10 total available? Like why did we do this?
1 second, where orders matter, 7 characters. I think, let me check it.
I guess it's written in the answer for the OTP one.
Pardon?
Yes, ma'am. The answer is for the OTP one, I guess.
Okay, yeah, I think I got it wrong here. I think this is for the 10P4, which is the OTP one, not for the, I'm sorry, okay? I'm sorry about it. Okay?
Yeah, ma'am, no problem.
Thank you for pointing it out. Okay?
So ma'am, okay, what would
I
be
did the
the
4-digit PIN code for that. This repetition is not allowed.
yeah,
Okay.
so but it's still 4-digit pin. Yeah, then it would be the right
Yeah.
one. But what about the first question? Like what
Yeah,
is
so
the
the
answer?
first one is 7 characters, right? 1, 2,
Yeah.
3, 4, 5, 6, 7. The same thing. How many ways? Only lowercase. So how many can I do here? Lowercase. A to Z is 26.
26.
And 0 to 9 is 10.
10.
Right? And I'm saying that I'm saying order matters, right? So this can be done in A to Z, and I'm not even telling whether see, when order matters and password, I think here I'm not mentioned about repetition. So I can have 26 plus 10, which is 36 into 36 into 36 into 36. Okay. But suppose I say repetition is not possible, then it would be 36, 35, and so forth, right? Now, suppose in many cases, okay, they will tell you that you cannot start with a 0 also, right? And they will also, many cases, I can say that the first 5 are characters and the last 2 are numbers. How many ways can it be done? So I have multiple ways of doing it. The question was, typically in problems of this kind, okay, you can have multiple. I'm saying the first 5 are 7 characters. First 5 would be alphabets, lowercase, and digits. How many ways can I do it?
7.
And you know that this is
7
36 to the power of 5 if repetition is allowed. If repetition is not allowed, it would be 36 into 35 into all of that. Into this would be 10 into 10 if 0 and 9 are there, or if it cannot end with begin with a, here I don't care if 0 and 9, so it would be 10 square. So you can see the multiple ways of forming this permutation.
Ma'am, what the first condition did you say? For the first 5
I said, see, let me give you the different conditions of password. If you see in any password, for example, if you're asking to set for a password for a bank, okay, internet of this one, you'll see that in many cases they say that use only uppercase, lowercase, and a number. Some places this is specified, yes or no?
Yes.
Okay. Now
Yes, ma'am.
I am telling you that this can be in any order. I can have A, 5, B, C, D, E, F, 1, 2, 3, 4, 5, D, E, 7. This is a valid password. Yes or no? Because I've used 5 letters and 2 digits. Right? And
Yes,
no
ma'am.
repetition.
Yes, ma'am.
But if I allow repetition, A is also a valid password, but this is a useless password. Most of the cases, this is not allowed also, right?
Yes. Yes.
So if I'm not allowing repetition, which answer is 720, please?
Ma'am, the bookshelves, the number
Okay,
is.
let me finish this and come back to that.
Yeah.
Okay. So if I'm not allowing repetition, so you can see that the total number of choices available is 26 lowercase plus 10 digits, which is 36. So 36 into 36 into 36 to the power of 7 would be the total number of ways I can do these passwords. Agreed?
Yes.
Okay.
Yes, ma'am.
Now I can make many more things. I can say that the first 5 are letters and second 2 are digits. Agreed?
Yes.
Now I want to just add some more masala. I would say that at least one of them is an uppercase letter.
Then there would be cases, no? Then one would be
So
two.
there would be different cases. So I can have many variations for this problem. This answer is wrong, I agree. But I'm saying that you can have many variations for this problem. Is that clear? But everything is a permutation. Okay?
Yes, ma'am.
You can have many variations for this problem. I can bring the special characters also. And I can tell you what are the special characters that are allowed. Exclamation, and, dollar. I can allow these 3 special characters. Okay. I can have now 7 characters using lowercase, digits, and special characters. So I cannot have only lowercase. I should have at least 1 digit and 1 special character. Right? So it is just complicating it more. At least 1 digit and 1 special character. Is this clear? So I have only 5 of this which can be filled up with alphabets. At least 1. Then I can have 2. So you can see that it will become a very messy thing. 2 digits and 1 special character. 3 digits, 1 special character. All of that you'll have to enumerate. Is that clear?
Yes, ma'am.
Yes, ma'am.
So the answer to this particular question would be 36 to the power 7 if the repetition is allowed.
Yes. Just only the plain vanilla thing.
And if its repetition is not allowed, it would be 36p7.
36p7. Yeah. Right. Yeah. What was this question? If I want to arrange 5 books, 8p5 and 8q5. That's it. Is that clear? This is 8p5.
Yes, ma'am.
8q5. Whatever is I do not know what is the numerical answer, but that's the answer. Okay. Is that clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Ma'am, I had a doubt on circular permutation. Like whenever there is a problem based out of like English, like the major plays of English, like there are 12 team members and a coach is sitting in between, vice captain and captain. So is like if we go by the conventional method, the coach is not considered in the team members list of 12.
Okay.
So there is like just the 12 team.
Is it a specific question from an activity or?
Yeah, there is in the graded assignment question, there is a question.
I will not be taking the graded assignment questions. Okay, I think that's requested. I will not be taking, but just look and see. I agree that you should first understand the question and that matters, but graded assignment, I cannot be taking it here. Suppose they're asking you that 5 people are sitting and in a team, the coach is sitting at the head of the table. So there are many things where the head of the table is fixed. Okay, and the only others are shifted. So this one position could be fixed, right? and only others are changing. So that would be it would not be anymore this person's position is fixed. Okay, that could be the head of the table position and things like that. Okay, I think I'll not take specific activity questions here. I'm sorry. Okay.
No problem.
Yeah. Okay. So now let's go ahead with. Are there any more conceptual level understanding for permutation and combination? We'll go ahead with probability. Okay. Now, when we are talking about probability, typically what is expected, and I'm going to just dive deep into this this probability tree part. Okay. So when I have building blocks of probability, I start with what is called a random experiment. And a random experiment could be problems which is I have a sample space. So I have a sample space which is the outcome of the sample experiment. Okay. This is the sample space. If I toss a coin twice, my sample space is HH, HT, TH, TT. Now we can have multiple sample spaces. For example, if I am looking at the time taken for a person to reach office from home. Now, is this certain or is this uncertain?
Uncertain.
This is uncertain. So it could be anything. And the way I can write that is, it could be anything between 0 and some time t, where t or 0 to infinity. This could be my sample space. It is a continuous sample space. It could be any time, right? Or it could be between 15 hours or 20 hours, but 0 to infinity is also fairly good enough. So you can see that I can define as random experiment and the sample space, which is outcome of the sample space. Now, let me come back to this tree later. But when I define what are the important building blocks, once I define what is a random experiment and a sample space, I need to understand what is an event. Okay, so given a sample space, defining these events become extremely important. And I need to understand the following. A sample space is a set. Events are subsets of the sample space. So even these are sets. So the minute I talk about events which are sets, all the basic set operations, namely union of events, intersection of events, complement of events, can be defined, right? The minute I define about if I define an event as a subset, I know that I can talk about union, I can talk about intersection, I can talk about complement. So the idea is, again, this is the abstract notion. Set itself is an abstract notion. Events are also abstract notions, but I am using this abstract notion to define from my real-time experiences. Okay. For example, the tossing of a coin could be also has only two outcomes. What are the two outcomes?
Head or tail.
Head or
tail.
Right. Now I can define a similar experiment which has two outcomes, which could be a pass or fail in an exam. Yes or no?
Yes, ma'am.
Agreed? Yes,
Yes,
or no?
ma'am.
Right.
Yes,
Right.
ma'am. Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Define. So if I have, say, now I'm going to extend the logic that you have two papers. Okay. What are the possible outcomes? So I have a stat 1 and a math 1 paper. Okay, what are the possible outcomes of the examination that you're writing for stat 1 and math 1?
4, ma'am.
You could either pass in both. You could pass in one and fail in math. You could fail in stat and pass in math, or you could fail in both. This is the same as tossing a coin twice and getting H, T, TH, and TT. Agreed?
Yes, ma'am.
Yes, ma'am.
Here, let me assume that here the chance of you getting a head is same as chance of you getting a tail. But here, is it always necessary that the chances should be the same when I have only two outcomes? You're passing, and I hope the chance you pass is much higher than the chance you fail. Right? That is anything a teacher would hope for. It need not be the same, right? I
Yeah.
could say that this is about 90% and this could be about 10%. Right? Would you agree?
Yes.
Yes.
So you can, so the idea is we always get motivated through a simple example, but you have multiple situations where it can be ordered. For example, even any situation which has only two outcomes, good, bad, defective, non-defective, approved, non-approved, all of them can be modeled basically on the two, or these are what we call Bernoulli trials, and this is what typically you would meet in a different, that is when you're doing random variables. But the more important thing is, this is just not stopping at abstraction. Knowledge of probability is extremely important for us to model a lot of real life situations. So in the basic probability, we need to understand how to come up with a sample space and how to assign probabilities of the events. So let's look at the simple example when I'm tossing two coins. I know what is my sample space. My sample space is HH, HT, TH, and TT. I have defined two events here. E1 is head in the first toss and E2 is head in the second toss. Can you all give me a few more events? Say E3, E4.
Ma'am, HHTT, HTHH.
Both are heads, yeah.
Define
Both
the
heads,
event.
both tail.
Define the event.
What, ma'am?
At least one head is there.
Only head comes.
Both heads.
All heads.
Both.
So that is just going to be HH.
Yes, all.
Head on both tosses.
Yes, all tail.
Head
All
on
tails,
first toss.
which is TT, right? Anything else?
Tail on the first toss
Tail on the first toss, which
and
is
head on the first toss.
and TT.
Head on the second toss.
So how many events can I define? HT, TT. How many events can I define? And I already said that events are subset of your sample set, right? So this is, have you all heard of the notion of a power set?
32 events?
Yes, ma'am. Max.
What is a power set now?
Ma'am, a set of all the
A set of all the subsets, ma'am.
Set of, so how many subsets?
The power 4. It will
Ma'am,
be
16.
2
raised to power 4.
Ma'am, 16.
Yes.
16 events.
So all these are your events. Is it clear? Okay.
Yes, ma'am.
Yes, ma'am.
When I'm interested in defining events, don't look at math separately, stats separately. All these concepts are related. Okay. Right. So you have learned already these concepts in your math. It was just using that concept. But again, when I talk about probability, I'm not interested in the set algebra. I am interested in applying these concepts. Okay. So for example, I have the sample space. Again, let's go back to our examination of Math 1 and Stat 1. These are the possible things that I fail in both, I pass in both. So now can you tell me what is the possible events that could happen? Instead of tossing a coin in terms of the results of the examination. Just describe the event and tell me whether it makes sense to have such an event. Describe one of the events.
Pass in stats and fail in maths.
Okay.
Passing both subjects.
Passing in
Fail
both.
in both subjects.
Failing
least
in both
pass in
subjects,
one.
passing
Passing in
both
math
subjects.
and failing in stats.
Right. So you can see that there is a meaning in the way we have constructed it. And when I am talking about it from this perspective, immediately we are interested in these chances happening. We might not be interested in tossing a 2 coin, but we are interested in something of this kind happening. Is that right?
Yes.
So that is where the modeling is. Modeling is always trying to look at a real life situation and see what is the thing? I love this concept. Can I apply the same concept to model this? Is it clear?
Yes.
Yes.
Okay. Right. Now, just as I define many events, and I know that these are subsets, I can define union and intersection of events. Now, union of intersection of events will also be one of the events I have defined. For example, if you look at the event, even union E2, okay, it is a HH, HT, and TH. Describe this event. Describe it. See, union from a set perspective is very easy. How would I describe this event?
Elements which are both in E1 and E2.
No, describe it. Elements which are both in E1 and E2, I agree. Describe it. That is a map definition, but I want you to describe it.
At least one toss.
Head on the first toss and
or
head on the
that is where the English language plays the thing. It is not about English language, it is in any language, right? This or and again go back to your addition rule. Addition rule was or and
or for at.
rule was and, right? Always remember union is or, intersection is and.
And.
Here?
And yes, ma'am.
Addition, union, or. Multiplication, intersection, and.
And.
Yes,
ma'am.
Okay. So whenever so now when I'm looking at, so you can see head on the first or head on the second is the union. Head on the first and head on the second is the intersection. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes.
So this is about events. And then one most important thing is the null event, which is no outcomes and the complement of an event. Now, what is the complement of E1?
O1 minus event.
Complement, yeah, but describe the event.
Tail on the first toss.
No,
tail on the vote toss.
It is
Tail
basically
on the first toss.
At least one head.
Right, tail on the first toss is your event, precisely your E5.
head
E5 now.
no head on the first toss. This is
Or tail on the first. What is even union E5?
Even union.
Even union E5.
The sample space.
The sample space.
Yes,
So when I look at only E1 is the event head on the first toss. E5 is my event tail on the first toss. Now these two are mutually exclusive. I cannot get a head and a tail in the first toss. Agreed?
Yes, ma'am.
They're joined. So events of this kind, E1 and E5, are called mutually exclusive and collectively exhaustive because they are giving, even union E2 is giving me the entire sample space. Is it clear?
Yes.
No, ma'am.
Yes.
E1 and E2 are
Sorry,
just giving
sorry, even and E5. Even and E5, I'm sorry. Even and E5. Okay, even and E5 are mutually exclusive and collectively exhaustive. Is that clear?
Yes.
Now let's look at even and E2. Are they mutually exclusive?
No, ma'am.
No.
They have a intersection, right? And that intersection is HH. Is that clear?
Yes, ma'am.
Yes, ma'am.
Right. So mutually exclusive events are very, very important. It says that E and F cannot simultaneously occur. Okay. Now, again, we have looked at the complements of the event and the subsets of an event. The Venn diagram is a very, very powerful tool for us to describe it. Just as when you have learned about sets, you have learned about Venn diagram. I can represent the events as subsets, the sample space as my universal set. That from mathematics, you would have learned it as universal set. And I know that E and F, here E union F is my, this one, E intersection F, that shaded region which is slightly darker is my E intersection F. These are two disjoint events. E is a subset of F. All of these are important because now we are going to set up the probability of an event. This is what we are interested in. What is the probability of an event? Now, probability of an event follows what is called the probability axioms or the axiomatic approach, which says that for any event, the probability of the event, the first axiom says that 0 is less than or equal to probability of any event is less than or equal to 1. The second one says the probability of a sample space is equal to 1. And the third one says the probability of your union. And here I have countable union is equal to the sum of the probabilities of the events. Probability of union is sum of probabilities. But the condition I require for them is for a sequence of mutually exclusive disjoint events. Now this mutually exclusive disjoint events, I can look at a finite union. This was a countable union because you have already looked at mathematics. You know the difference between countability and finite union. I hope you all know about it. Yes? Can I assume?
Yes, ma'am.
Yeah.
Yes, ma'am.
Yes. Look at a finite union. I can extend this that E1 union E2 is a finite union. If E1 and E2 are disjoint, the probability of the union is the sum of the probabilities. Now this further, if E1 and E2 were not disjoint, I can look at probability of E1 union E2 is the probability of E1 plus probability of E2 minus probability of E1 intersection E2. And the way we proved it in the lectures are, we looked at this as E1, this as E2. We looked at these three sets, which I have shaded in different ways. So the vertical bar, the horizontal bar, and the dotted. Now these three are mutually disjoint, right? I can write this as A, this as B, and this as C. So probability of E1 union E2 is probability of A plus probability of B plus probability of C. Would you all agree?
Yes, ma'am.
Yes, ma'am.
I write A in terms of E1 and E2, B in terms of E1 and E2, C in terms of E1 and E2 to get this expression. Is that clear? This is what is referred to as the addition rule of probability. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
When E1 and E2 are disjoint, this would be E1 intersection E2. If E1 and E2 are disjoint.
Yes.
E1 intersection E2 is null. And probability of the null set would be 0. Okay. So the probability of E1 union E2 would be just probability of E1 plus probability of E2. So these are what are called probability axioms. And from the probability axioms, we have what is called the addition rule of probability. Okay. So for example, let's go back to our shirt and pant example. Suppose how many shirts did I have? I had 3 shirts. Suppose the chance of you buying a shirt is 0.3. And the chance of you buying a pant is 0.2. Okay. And the chance that you'll buy both a shirt and a pant is 0.1. What is the proportion that purchase neither a shirt nor a pant? So let's define the event. What is E1 or S here? S is the event of a customer purchasing a shirt. What is probability of shirt given to you?
0.3.
0.3. E is the event of a customer purchasing a pant. That is given to be 0.2.
0.2.
What is this 0.1? It is probability of
Intersection.
S intersection buying both
Pant and shirt.
And right. Now I'm asking what is the proportion that buys neither a shirt or a pant? What is the proportion that buys a shirt or a pant?
0.4.
0.4.
That would be 0.3 plus 0.2 minus 0.1, which is probability of S, plus probability of P, minus probability of S intersection P. This is my addition rule. Yeah?
Yes, ma'am.
But that is not what I want. This is either a shirt or a pant. I want neither a shirt nor a pant. So what am I looking at? In the complement of this event. Agreed?
Yes,
and that is going to be 1 minus 0.4, which is 0.6.
0.6. Yes, ma'am.
So here we have used the individual probabilities, the intersection probability for my addition rule, and the complement rule, which is probability of S union P complement is 1 minus probability of S union P to come up with the answer. Is that clear? So identifying the events and what, so here, see, The addition, intersection, union and everything is how you are going to translate what is given to you into math. Again, shirt or a pant is S union P. Shirt and a pant is S intersection P. Neither shirt nor a pant is S union P complement. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay, right. So the next thing is what is equally likely. And for this, we always look at rolling a dice experiment. Okay, even in a tossing a coin, I have only two outcomes. And if I assume that head and tail are equally likely to happen with probability half and half. Now, when I roll a die, okay, the sample space, hello?
Yes, ma'am. Yes, ma'am.
Hello?
Yes, yes, ma'am.
Not for me. Okay, right. So I roll a fair dice. The sample space is 1, 2, 3, 4, 5, 6 because these are the possible outcomes that can come. Okay. So since the dice is fair, I know E1, E2, E3, E4, E5 is just 1 by 6. Probability of E1, probability of is equal to probability of E2. It is equal to probability of E3 is equal to probability of E6, which is equal to 1 by 6. Now, suppose I want to, A is the event that the outcome is odd. I know that the probability of A is nothing but probability of E1 plus E2 plus E3, which is 3 by 6, which is 1 by 2. Now, C is the event that the outcome is either odd or greater than 4. B is the event is greater than 4. So, what is the probability of B? The
Probability of
outcomes
union.
are 5 and 6. So probability of A is 1 by 2. Probability of B is 2
1
by
by 3.
6. Okay, so this is nothing but 3 by 6. I want to know that it is either or. So it is either A or B. So what is the intersection of A and B? Are they disjunct or is there an intersection?
There is an intersection.
There is an intersection.
Intersection.
An intersection.
That's 5.
So probability of A union B is going to be 3 by 6 plus 2 by 6 minus 1 by 6, which is 4 by 6. Is that clear? Again,
Yes, ma'am.
application of your addition rule in equally likely events. Okay. Now, before I go here, let me show you this to tell you the difference between an equally likely or not equally likely events. So consider tossing a coin once. I have two outcomes, which is a head and a tail, and I can represent it using this probability tree. Okay. The probabilities of the events happening, that is the outcomes happening, is 0.5 and 0.5. When I toss a coin twice, I have what are the possible outcomes? I have a head and a head, which is here. I can write this outcome gives me head, head. This is a head, tail. This is a tail, head. And this is a tail, tail. Now, what is the possible outcome of a head? This is my first toss. This is my second toss. What is the probability of getting a head? Fair toss. This is 0.5.
1 by 2.
Also 0.5. This is also 0.5. Second toss getting a head is 0.5. Second toss getting a tail is also 0.5. So these are the probabilities of that outcomes happening. Now I'm interested in knowing what is the probability of HH, HT, TH and TT happening. Now the probability of any event happening. So I'm interested in head in the first toss and tail in the second toss, or head in the first toss and tail in the second toss, or tail in the first toss and head in the second toss, or tail in the first toss and tail in the second toss. These are the probabilities I'm interested in knowing. Would you all agree?
Yes,
ma'am.
Right. So similarly, if I look at this particular thing, I have a bag with 3 black and 4 white balls. I'm picking up one ball. Okay, what are the possible outcomes of this experiment? I'm picking up one ball. What are the possible outcomes? And noting its color.
Can be any of the two colors.
So that would be either a black ball or a white ball. Now, what is the chance of me picking up a black ball?
3.
3 by 7.
3 by 7.
Right? What is the chance of me picking up a white ball?
4:7.
4 by
4 by
7.
7. So are these two? So suppose I am calling E1 is the event of picking up a black ball, and E2 is the event of picking up a white ball. Are E1 and E2 equally likely outcomes to happen? Or
No,
even
ma'am.
they are not equally. That is the main thing which I wanted to convey. Not all the outcomes have to be equally likely. Is this clear?
Yes.
Yes, ma'am.
Right. So now suppose this is my, so what I'm trying to say is I have 4 white and 3 black. I pick up one, okay, black. What am I doing? If I pick up a black ball, I'm going to a bag 2, okay, which has 3 white and 6 black balls. If I pick up a white ball, I'm given a bag which has 4 white and 5 black balls. Okay, I'm given different bags. Okay, now what is the chance of, what are the possible outcomes I have here? The second thing, I'm again picking up a ball. Again, what are the possible outcomes from here?
From which bag, ma'am?
I could either, from either of the bags, right? I could either pick up a black or a white. I could again pick up a black or a white here also. Now, what is the chance? So finally, what are the possible outcomes? My first one could be a black ball, second could be a black ball, which is this. My first is a black, second is a white, which is this outcome. My first is a white, my second is a black, which is this outcome. My first is a white, my second is a white, which is this outcome. Is that clear?
Yes, ma'am.
So if I ask you the question, what is the chance of me getting 2 black balls in both the outcomes? I'm interested in knowing the probability B1 intersection B2.
Ma'am, 1 by 3.
Yes, 1 by 4.
7.
1 by 4.
No, I'm not asking. I'm first of all writing it as an event. Is it clear?
6 by 9 and 5 by 8.
No, I'm not asking for the number. I'm telling, is that the same as getting 2 black balls? Is this even probability of a black in the first and black in the second, right?
Yes, ma'am.
Now, the way we can write this probability is probability of me. So that's why I need to introduce the notion of a conditional probability. Now, getting a black in the second, the probability of getting a black in my second row, does it depend on whether you had a black in the first row or a white in the first row?
Yes, ma'am.
No.
Yes, ma'am.
No, ma'am.
Yes or no?
No.
Yes.
How many say yes?
Yes, ma'am.
Yes,
Can
ma'am.
you
The
repeat the
probability
question?
of getting a black in the second row, does it depend on whether I had a black? What is the probability of getting a black in the second row when I had a black in the first row?
5 by 9, ma'am.
2 by 8.
6 by 9.
6 by 9.
Given I had a black in the first row, what is the chance of me getting a black in the second row?
5 by 7.
5 by 9. 5 by 9.
2 by 7.
Why is it 5 by 9?
5 by 8.
5 by 8.
Yes.
Because I already picked 1 ball.
See, black in the second row, given black in the first row is 6 by 9, right? 6 over 9.
Yes,
Black
ma'am.
in the second row, given white in the second row, it's 5 by 9. Is it clear?
Yes.
So, ma'am, how is it 6 by 9, ma'am, if you can explain?
See, I'm asking black in the second row, given I had a black in the first row. Is that right?
Yes.
Yes.
So black in the second row. So this is the only thing I need to check. Because this is a white in the first row.
Yes, ma'am.
Okay. If I get a black in the first row, I'm asking you to choose a black from this bag. I'm not telling anything about the bag. I'm not going back to this bag. That's why I said bag 2.
Yes, ma'am. Yes, ma'am. I thought it is bag 1. That's why I was saying 2. I
clearly said bag 2. That's right.
Yes.
The bags are different. If you get a black in the first bag, then you're going to bag 2. They're different bags.
Yes, ma'am. Got it.
The thing is, you have problems of, okay, if I get a black, I'm adding a white. If I get a white, I'll add a black and remove the black. You have seen problems of this kind also, right?
Yes.
Yes, ma'am.
If I get a black, I'll remove that black and I'll add one of the other color. So if I get a black, what would I have here? I'll have 5 white and 2 black, right?
Yes.
If I get a white, I'll get 4 white because I'm removing 3 whites and 4 blacks, right? If I get a white, because I'm adding one of the other kind and I'm removing this color. You would have seen problems of this kind also, right?
Yes, ma'am.
Yes, ma'am.
Right?
Yes, ma'am.
Here I'm giving you another bag. Okay, if you get a black, so here what is the chance of me choosing a black? It's 6 by 9.
Yes.
Yes, ma'am.
If it is a white, it is 5 by 9. So the question I'm asking is, if V2 is the event of getting a black in the second throw or second draw, does that depend on whether I had a black in the first or a white in the first? That is the question I'm asking.
Yes, ma'am.
It is dependent.
Yes.
Now go back
Yes,
here.
ma'am.
Getting a head in the second toss, does that depend on whether I got a head in the first or a tail in the first?
No.
No.
Because they're equally like.
Not equal, don't confuse it. Yeah, it is equally likely, but it is not dependent also, right?
Yeah.
Is it clear?
Yes, ma'am.
Yes, ma'am.
Separate events.
See, my chance of getting a head in the second toss does not depend on whether I got a head or a tail in my... See, if you look at it, this is the same thing, right? I had 2 outcomes, black and white. Black and white, black and white. The tree structure is the same.
Yeah.
Yes, ma'am.
In one, the black in the second is dependent on whether I had a black or white in the first. The second one, the black in the second, head in the second does not depend on whether I had a head or tail in the first. Is it clear? Notionally, at a conceptual level, is that clear?
Yes, ma'am.
Yes.
Yes, ma'am.
Have something which are
Yes,
called
ma'am.
dependent events and independent events. So to get this notion, we are introducing what is called a conditional probability. That is, what is the chance of an event happening conditioned on another event? So what am I asking? What is the chance of you getting a head in the second toss conditioned and you had head in the first toss? What would this be? This would be the same as the getting a head in the second toss. Would you all agree with me?
Yes, ma'am.
But in this example, what is the chance of you getting a black in the second toss given black in the first toss? Is it the same as getting a black in the second toss?
No, ma'am.
No, ma'am.
No, ma'am.
Not the same. So when I have 2 events, now I define a conditional probability, which is probability of A conditioned on B is probability of A intersection B divided by probability B. So if I have 2 events, okay, and I'm conditioning A happening given that B has happened, so I'm interested. So this is B and this is A intersection B. This is the probability of how much of this A has happened conditioned on B. It is the probability of A intersection B divided by this entire probability. Okay, so if A and B are independent, probability of A conditioned on B is the same as probability of A because that's what we saw. Agreed? The conditional probability is the same as the unconditional probability. Agreed? So what do I get? I'll get probability of A intersection B is probability of A into probability of B. When I have 2 events, this is what is called my condition. So you see that in general, I saw that probability of the union is probability of E plus probability of F minus probability of E intersection F. This was my probability of E. This was my probability of the union, which I referred to as the addition rule. Agreed? So for any 2 events, the probability of the intersection is probability of E conditioned on F into probability of F. This is what I have, the probability of the intersection, which I refer to as my multiplication rule. Because addition is union. Again, remember, or addition, union, and multiplication, intersection. Is this clear?
Yes, ma'am.
Now,
Yes,
when
sir.
E and F are
Yes, ma'am.
independent, probability of E conditioned on F is same as probability of E. So I get, when I have independent events, I get probability of E intersection F is product of the probabilities. When E and F are disjoint, probability of the union is addition of the probabilities, because E intersection is 0. Is this clear? Let me repeat. I have two notions. One is the notion of disjoint. One is the notion of independence. Disjoint is also same as mutually exclusive. Is this clear?
Yes, ma'am.
Yes, ma'am.
So in general, when I am talking about union, I have the addition rule, which is probability of E union F is this. I'm just looking at two events. I can extend it to multiple events, but for a conceptual understanding, I'm looking only at two events. And the multiplication rule is given by this. Till here, is it clear?
Yes,
Yes,
ma'am.
ma'am. Yes,
If
ma'am.
I have disjoint events, what would happen to E intersection F? When two events E and F are disjoint, this E
Five.
intersection F is null. So this will go to 0.
Empty.
Yeah.
Yes, ma'am.
So what will happen to probability of E union F? It is nothing but probability of E plus probability
Plus
of
probability of F.
F. Right? Now, when I have two independent events, what will probability of E conditioned on F be if E and F are independent? This will be just probability of E, right?
Yes, ma'am.
So when I have two independent events, the probability of E intersection F is the product of my probabilities. Here, if I have disjoint, the probability of the union is sum of probabilities. If I have independent, the probability of intersection is product of probabilities. Addition, multiplication. Intersection, multiplication. Union, addition. Union is with disjoint, intersection is independent. Is this clear?
Yes, ma'am.
Yes, ma'am.
Wanted to spend some time because these are disjoint, mutually exclusive, and independent are very, very easily confusing notations for a lot of learners. They get mixed up between these two. I hope you understand. Independent is different from mutually exclusive. Is it clear?
Ma'am, in case of independent, what is the probability of E union F?
It would be the same thing, right? If it is independent, then it would be probability of E plus probability of F minus probability of E into probability of F. That's it.
Okay.
Okay. Because probability of E intersection F is probability of E into probability of F, right?
Okay, ma'am.
Yeah. Okay. So I can generalize this multiplication rule. So going back, if I use this independence rule, so I have probability of B1 intersection B2, okay, would be nothing but probability of B2 given B1 into probability of B1. What is probability of B2 given B1? It is 6 by 9. Probability of B1 is 3 by 7. So this is 3 by 7 into 6 by 9. Is that clear?
Yes, ma'am.
Yes, ma'am.
Now, when I'm looking at probability of H1 intersection H2, okay, this is the same as probability of H2 given H1 into probability of H1. But what is probability of H2 given H1? It's the same as probability of H2 into probability of H1, right? Which is 0.5 into 0.5, I get a 0.25. Is that clear?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
0.25. This is a 0.25. All of them would be 0.25, 0.25. And you can see that this all would add up to 1. Okay. This 0.25, 0.25, 0.25, 0.25. Similarly, here also all of them would add up to 1 because these are finally, this is my total, my sample space is getting a B1, B2, B1, W2, W1, B2, and W1, W2. This is my sample space, right? and all of them should add up to 1. These are the probabilities of the events. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now the last topic is moving from conditional, this one, we introduced independence event. We are going to go to what is the Bayes theorem. Okay, and I'll stop with this. So the Bayes theorem, see, for example, if I have the following, this is my sample space, okay, and I'm having 2 events. This is, let me go back to one of the examples which we defined, or let me go to this example itself. I'm having a company, okay, which is getting its raw material from 3 factories. Let me call it A, B, and C. This is 40% of my raw material comes from A, 30% comes from B, and 30% comes from C. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
I pick up a material at random. What is the chance it comes from factory A?
1/3.
0.4, right?
Yeah.
Yes, ma'am.
What's the chance that it comes from B?
0.3.
0.3.
Chance it comes from C? It is
0.3.
0.3.
So these are what I refer to as the prior probabilities. That is, I'm looking at a company and I know that these are all my raw materials, okay, materials. So suppose I am a car manufacturer and I'm looking at, say, some material. I have 3 suppliers. They are supplier A, supplier B, and supplier C. A sends me 40% of my total requirement. B sends me 30% and C sends me 30%. This is a chance. I pick up one of this material at random. What is the chance it comes from A? It is 0.4. Chance it had come from B is 0.3. Chance it had come from C is 0.3. Till here, is it clear? These are what we refer to as prior probabilities. Till here, is it clear, please?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now, I have further
Yes, ma'am.
that not everything from each of these factories are good. I have, if an element comes or if a material comes from factory A, there's a chance of it being defective, and I say the probability of it being defective given that it comes from A is 2%. Okay, 2%. So A says that I am good, but 2% of the what I'm supplying is defective. B says that the chance is 0.03%, and C says it is 1%. Okay, sorry, D given C. Is it clear? These are the chances of the material being defective. So if I define D to be the event, so I have, say, 100 elements that have come. I pick up one element at random and I see that it is defective. What is the chance that it was going to be defective? I repeat, I have 100. Imagine I have 100 items that have come to me. I mix all of them together and I pick up one. What is the chance that it would be defective? That is the first question I want to ask. Okay. So this is the event of it being defective. Is this clear?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Defective, and it could come from A. That is this portion. This portion which I have shaded is it is defective and it comes from A.
Yes, ma'am.
Now
Yes,
this
ma'am.
it is defective and it comes from B.
Yes, ma'am.
And this is it is defective and it comes from C.
C. Yes, ma'am.
I want to know what is the chance that it is defective. I can write this D as D intersection A, union D intersection B, union D intersection C. Can I do this?
Yes, ma'am.
Now I can apply are D intersection A, D intersection B, D intersection C mutually disjoint?
Yes, ma'am.
So can I apply the addition rule?
Yes, ma'am.
Yes, ma'am.
The probability, this is what I was interested in knowing. So the probability of this is probability of D intersection A plus probability of D intersection B plus probability of D intersection C. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
But what is probability of D intersection A? My multiplication rule, what does it say?
Probability of D into probability of A.
Probability of D given A into probability of A. This is what my multiplication rule says, right?
Yes, ma'am.
Plus probability of D given B into probability of B.
Yes, ma'am.
Plus probability of D given C into probability of C. Do I have all these values with me now?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Can I find out what is the probability of the defective?
Yes.
Now, this is what I refer to as a total probability rule. Is this clear?
Yes.
Yes, ma'am.
Yes, ma'am.
Yes,
You
ma'am.
can find out what is the chance. So, imagine I have 100 items. I pick up one item at random. I want to know what is the chance with which it is defective. Using this information, I can find out what is that using my total probability rule. Till here, is it clear?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Now, I'm going to define the next thing. I have all these 100 items. I mixed it up. I pick up one and I notice that it is defective. Okay. I know. So what is given to me? I know that it is defective. Now, I want to know what is the chance it has come from A. Now, what is the difference between this and this event? What is probability of A?
0.4.
Point
0.4.
0.4. But how did I define it? See, I got 100 items from these three places, right? I pick up one item at random. The chance that item comes from A is 0.4, right?
Yes, ma'am.
40. Yeah.
Now I have got some extra information about this item. And what is that information I have got about this item?
It is defective.
It is defective. So now I want to know what is the chance that it came from A given it is defective. This is what I refer to as posterior probability. This was my prior. I said these are my prior probabilities. This is my posterior. And what is the posterior? What is the chance it came from B given it is defective? What is the chance it came from C given it is defective? Is this clear?
Yes.
Yes,
Ma'am, can you
ma'am.
repeat again?
See, earlier, imagine I get 40 items from company A, 30 items from company B, and 30 items from company C. That is 40%. Okay. I am mixing all of them together because they are identical items.
Okay, ma'am.
I am picking one at random.
Yes, ma'am.
There is a chance that whatever I have picked has come from B.
30%, ma'am.
30%. Till here, is it clear? This is my prior probability. Okay. Now I also know that in this 100 items, there could be defective items. Not all of them are good.
Yes, ma'am.
What is the chance of me finding a defective if it is from A? What is the... I know 2% of my items from A are defective, right?
Yes, ma'am.
Yes, ma'am.
I know 3% of B are defective and 1% of C is defective. That's what I've written as conditional probabilities, right? Here is it clear? But now I'm again mixing up all these items and picking up one item. What is the chance it is defective? I'm using this rule here. This is what we call the law of total probability. I could have an item which is defective, which is from A or from B or from C. That is what I write as D intersection A, union D intersection B or D intersection C. A
So you
defective
have mixed up,
from all. Yeah.
you have mixed up all the defective items, ma'am.
Mixed up all the items and I picked up one. I want to know what is the chance with which it is defective. It could be good or it could be defective, right? What is the chance with which it could be defective? That is the question I'm asking.
Okay.
So an item can be defective and it can come from A, or it could be defective and it could come from B, or it could be defective and it could come from C.
Yes, ma'am.
That's what I've written as D intersection A or D intersection B or D intersection C. Is it clear?
Yes.
And that's how I
Yes,
found out the probability of the defective. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
I can work that out. That would be 0.4 into 0.02 plus 0.3 into 0.03 plus 0.3 into 0.01. That would be the probability of the defective. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Now, I'm telling that I am mixing up all these and I pick up an item and I notice it is defective. Okay. I notice it is defective. I want to know what is the chance. So, okay, let me put it in another way. Suppose this were 3 colleges from which people are coming to the IIT online degree program. Okay? Assume. Okay? And I know that there is a, so from college A, how many people are coming?
0.4.
40% are coming from college A, college B, and college C. What is the chance a person will fail given he's coming from college A? There could be a person who could fail.
Yes, ma'am.
That is 2%, 3%, 1%. So I am finding pick up a person at random. What is the chance with which that person will fail? That is going to be this. Agreed?
Yes, ma'am.
Yes.
Okay, till here is it clear? Okay,
Yes,
now I know a person has failed the exam. That is the information that has come to me. I want to know what is the chance that he has come from college A. So how would I write that?
Probability D comes
Of
from
A
A.
condition that he has failed. Is that right?
Yes, ma'am.
This is what I want to know. Agreed? Similarly, I
Yes.
want to know probability of B conditioned on fail, probability of C conditioned on fail. These are what are called, see, these are the prior probabilities, right? Probability of A, B, and C. Now I'm giving you extra information. What is the chance that a person comes from college A, given that person has passed or I'm looking at failing here because defective and failing, I'm just equating the two notions. Is it clear? That is what I want to know.
Okay, ma'am.
Is this clear?
Yes.
Yeah. So to compute that, what are we doing? So to compute that, what I do is the following. I know probability of A conditioned on D is nothing but probability of A intersection D into probability of D. This is from a conditional probability formula.
Yes, ma'am.
Yes, ma'am.
Yes. Now what is probability of A condition? This is probability D conditioned A into probability of A. My numerator.
Yes, ma'am.
Yes, ma'am.
Denominator I just found out was probability D conditioned on A into probability of A plus probability D conditioned on B into probability of B plus probability D conditioned on C into probability of C. That was what I just found out, right? Probability of defective. So
Yes, ma'am.
probability of A conditioned on D is equal to this. And this is what we refer to as the Bayes theorem. If you look at it, this is the Bayes theorem. Is this clear? I can
Yes.
extend to any number. So this Bayes theorem computes the posterior probability. Okay. Now, a very, very famous application of this Bayes theorem is what we call the Monty Hall problem. Okay. Monty Hall problem is nothing but a game show. Okay. Let me see whether I can pull out from one of my things the Monty Hall problem. Just give me a minute. Just give me a minute, please. This, 1 second. Okay, I'll tell you, I'll just show you what is the Monty Hall problem. Just give me a minute. Pull it out. Okay, I don't have it with me here, but let me explain the Monty Hall problem. So this is about a game show, okay, in which, okay, let me try and see whether I can share this one. Just a minute. I'll go. Let me stop sharing. Okay, you can type a thing called Monty Hall, but this is a Monty Hall problem. Suppose you are playing a game. Are you able to see 3 doors? Behind a door, there's a goat.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
This is called the Monty Hall problem, where I have goat behind 2 doors and a car behind a door. Okay, so if you are the participant, you are asked to choose one of the doors. Okay, right?
Yes, ma'am.
You are
Yes,
asked
ma'am.
to choose one of the doors. And suppose you have chosen door 1. Okay, I will open a door which will have a goat. Definitely there, if you, whatever door you choose, there will be a door behind which there's a goat.
Yes, ma'am.
Would you agree?
Yes, ma'am.
Yeah. So I will open a door and I'll show you a goat. Okay. The question is, will you, suppose you have chosen door 1 and I show you a
Ma'am, can you please repeat?
Yeah?
Can you please repeat?
1 second, let me show that problem. This is very small. I thought I'd show. 1 second, let me share a bigger thing. Just give me a minute. Okay, this is, can you see 3 doors? A blue door, a green door, and a red door, right? Can you see them?
Yes, ma'am.
Yes, ma'am.
You all to choose one of the doors. Which one will you choose? Choose. Anyone choose.
Green.
Red.
Red.
Blue.
Whatever you choose, I'm going to choose a door and show you a goat. That is possible for me? Yes or no?
Yes, ma'am. Yes, ma'am.
Right. The question is, after showing you the goat, I allow you to either stay with your original choice or swap your choice. So if you have, suppose you chose blue and I opened the green door and showed a goat, would you go for a red or would you retain the blue? That is the question. That is a Monty Hall problem. What do you think you would do?
Retain for blue.
Retain with red.
Would you swap or would you retain?
Retain.
Why?
Retain.
Ma'am, what is the end solution, ma'am? Like, we need to get a goat or we need to get an empty room?
There's a car behind one of the doors.
Car.
If you
Okay.
want a goat and not a car, that is your problem.
Okay.
Okay, there's a car behind one of the doors and goat behind 2 doors. What would you choose? Think about it. I will not tell you the solution. There is so much. If you just type Monty Hall, okay, you'll find that there are so many things written about Monty Hall and everything in your entire this one. There is so much written about Monty Hall problem and how interesting and how people can solve the problem using conditional probability and Bayes theorem. Okay. So with that, I think I come to an end of today's session. Thank you all and wish you all the best. I hope you found it useful. Yeah. Thank you.
ma'am. Thank
Thank you, ma'am.
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 Thank you.
Thank you.
Thank you, ma'am.
Thank you all.
Thank you, ma'am. Goodbye, ma'am.
Yeah, ma'am.
Bye bye and thank you.
Thank you, ma'am.
Thank you. Thank you all.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you. Have a good weekend. Yeah.
Thank you, ma'am.
Thank you. Thank you all. Thank you. So Prashant,
Bye,
I'll
ma'am.
share the slides with you. You can share it with everyone. Okay?
Yeah, sure, ma'am. Sure, ma'am. We'll share.
Thank you. Thank you.
Thank you,
It's-
ma'am.
Thank you, ma'am.
Bye.
Thank
Bye,
you.
ma'am.
Bye bye.
Bye-bye, ma'am.
Bye everyone. Take care. See you all later. Bye.
Bye, ma'am.
Bye, ma'am. Thank you, ma'am.
Hello. Did the ma'am leave? Hello. Hello. Can we leave the meeting?